Hello, this video is on all the different kinds of forces and Newton's third law. The essential question is, what does the size and direction of a force depend on? So when in our last unit we were talking about collisions and explosions and objects changing momentum. The way objects do that is by exerting forces on each other. So when a force is exerted, objects change momentum, as we kind of discovered from our equation that we came up with before. Now the really interesting thing about this force is explained in Newton's third law, and it basically says that whenever two objects touch each other, both objects are impacted equally by that force. In other words, every time you touch something, it touches you back with the same amount of force. If you are, holding hands with your mom, you can feel her and she can feel you. And if you squeeze, it hurts her, but it also hurts you. And that's basically the idea with Newton's third law. A way to write this a little bit more technically, these two fingers are touching. That hand on the right is hand B, and the hand on the left is hand A. There's a force to the right on hand B by hand A. But there's also a force on hand A by hand B. So they both feel each other. Those forces are equal in size. They both feel the same amount of force, and they're in opposite directions. So let's talk about some specific forces. As I said earlier, whenever we have a force, we're going to use a capital F, but we'll use a little subscript letter to tell us specifically what force we're talking about. Some of these forces you may be familiar with, and some you may not, but these are ones that we're going to be using in this class. The first, and probably the one that jumps out at everybody, is gravity, which we'll call F with a little g. Gravity is a force that acts between any two objects with mass. So if you had two peanuts in outer space, there would be a gravitational attraction between those two peanuts. They would actually be pulling towards each other, just like we're pulled to Earth right now. Of course, that's a very small amount of gravity because the peanuts don't have very much mass. If I have objects with more mass, like a black hole or the sun, and they were close to each other, there would be a much larger Fg than between the two peanuts. I do want to point out that the force of gravity is equal on each of those objects. So peanut A feels a force of gravity from peanut B, but peanut B feels the same force of gravity from peanut A, and that's due to Newton's third law, which we talked about in the last slide. The second force that we're going to be using all the time is called the normal force, and it's got a good name because it's actually a really normal force. It's probably most of the forces around you are actually normal forces. Normal forces happen when any two objects come into physical contact with each other. So you're sitting in a chair right now. There's a normal force between that chair and your body. Your clothes are touching your body. That's a normal force. The chair touches the floor, so there's a normal force between the chair and the floor. Small amount of normal force when the two objects are not pushing very hard. So if you give someone a high five, there's normal force between your hands, but probably not a lot, compared to the normal force between an airplane on the runway. Much more normal force because the airplane and the runway are pushing on each other a lot harder than your hands are pushing on each other with a high five. Third force is electrical force, or F with a little e. Electrical force exists between any two objects with charge. We'll talk about this more in our next unit, but between protons and electrons. And of course, if you have a lot of protons and electrons, it's more force. Friction is a very common force. FF. Friction acts between any two objects rubbing together. If those objects are smooth, like glass sliding on a desk, it's going to be a small amount of friction. Of course, if they're rough or they're pushed together really hard, like your knees on a sidewalk, that's going to be a much larger force of friction. Tension force, or FT, is a force between any two objects that are connected by a rope or a string. So when you're playing tug of war, that's a tension force. Your dental floss would be a small amount of tension force compared to a rope that's lifting up a piano. That would be a much larger amount of tension force. Spring force. So if Fs, for any two objects that are connected by a spring or a stretchy band, if you've ever ridden a pogo stick, that would be small amount of spring force. The shocks on a truck would be a large amount of spring force. And the most important thing about all these forces is that each one is an equal and opposite force interaction between the two objects. You'll notice I always mention two objects when I talk about force, because forces are fundamentally between two objects that are acting on each other. So when you consider all the forces acting on all the objects, it can actually get a little bit complicated. This is not a free body diagram. I just want to talk about all the forces that are acting in this picture of this person pushing a piano. So of course there's the force of gravity on the piano by the earth. Earth is pulling downwards on the piano, but Newton's third law says that the piano is also pulling upwards on the earth. So there's also going to be a force of gravity on earth by the piano, and those are equal in size and opposite in direction. There's a normal force on the piano by the ground, because the ground is touching the piano. The ground is pushing upwards on the piano. There's also a normal force downwards on the ground, so the piano is pushing down on the ground, and those two forces are also equal and opposite to each other. There's another normal force on the piano to the right, and this is caused by the person pushing the piano. He's making contact with the piano, so we have a normal force on the piano to the right by the pusher. But there's a normal force on the pusher back to the left, so the pusher's hands are feeling the force of the piano back in the other direction. There's also a friction force on the piano, acting in a direction opposite from the motion of the piano by the floor surface. So the piano's wheels are rubbing on the floor, and that's pushing to the left on the piano. Of course, the piano is also pushing on the floor, so the floor feels stretched by friction in the opposite direction. So these are all the forces on the piano, and also all the forces on the other objects that are touching the piano or acting on it. So now that we have a better idea about forces, the specific forces and where they come from and what direction they're acting, we can start to draw some new and improved free body diagrams. The one thing that's important on the free body diagrams is to realize that you should only include the forces on the object. So if I'm drawing a free body diagram of the piano, I only want to put in there the forces on the piano. All those other forces in the last slide would be on different free body diagrams because they're acting on different objects. From now on, when you draw your free body diagrams, you should include the names of the forces and the object causing them in all of your labels. It won't be considered a complete free body diagram if it doesn't have this. And as we mentioned before, you should make it obvious if those forces are balanced or unbalanced. So if this is the piano, I'm going to say there's a force of gravity from Earth downwards on the piano. There's a normal force upwards on the piano from the ground, and those two are equal to each other. There's a normal force to the right from the piano pusher, and there's a friction force to the left from the floor. Those guys are not equal to each other in this case, so I made the pusher a larger arrow than I made the floor. Reminder that this free body diagram tells us all sorts of things, but the most important thing that you can get out of this free body diagram is that sigma F, the extra force, the leftover force, is to the right. Up and down are canceled. The left cancels out some of the right, but there's still some extra leftover force to the right, which means that this piano's momentum is changing to the right, probably speeding up if the pusher is pushing harder than the force of friction. To summarize, what does the size and direction of a force depend on? Depends on the kind of force, but hopefully you guys can have a better sense of where those forces come from and how their size and direction can be determined. Thank you.